So today we're going to actually, I realized I'm switching up the order of the 2 lectures this week. The reason for that, I was going to do probabilistic modeling today and then big data Wednesday, but I changed it because I actually am porting over some of the code in the probabilistic modeling to work with PyMC3 instead of PyMC2. Hopefully the homework will be the same way. We may have to abandon that if not, if that isn't working on Autolab. But it's a more current and relevant framework, so you should actually know PyMC3 at this point anyway. So that was still in progress, so I actually decided to do the big data one today. So again, a couple quick announcements. The homework will be out on Wednesday. And then you'll have, as I said many times now, but it'll be described in the homework, you'll have an option of doing some portion of the problems, and it's meant to be smaller than the previous homeworks. All right, so today we're going to talk about any questions on logistics so far. The other thing, I guess, is your tutorial grading is due this Friday. If you have not verified your tutorial yet, looks okay on the website, please do that immediately. We are getting still some emails from people saying they're missing images, or something like that. So just fix those issues if there are any, and make sure it's sort of corrected, because people are going to start grading them other tutorials. So make sure your own is fixed. Any other questions or any questions? Okay, so let's jump into big data and MapReduce. And this is going to be like the other ones, kind of a one-off lecture, but this is a very important topic in data science. If not always in practice, then at least in how people talk about data science. So, and it is actually quite useful in practice as well. So we'll talk about both those things and kind of what big data is and focusing on this paradigm of the MapReduce system. So first of all, we're going to talk about big data. We're going to give some context for distributed computing as a whole. I'll talk about map and reduce, which are 2 functional primitives that are included in Python, for example, that are a good way of getting started with MapReduce, but which are actually different from MapReduce. So I'm going to talk then about MapReduce as the distributed computing paradigm, and then very briefly we'll talk about, I just want one slide showing how you do this kind of stuff in Python if you actually want to do it in practice. So let's talk about big data to start off with. This term gets kind of thrown around a whole lot in data science. It's a little bit, maybe a little bit less being replaced by AI these days, I guess, as the buzzword of choice amongst startups and VCs in Silicon Valley. But it's still a very common buzzword, and I think for a long time was misused repeatedly, right? Where everyone wanted to be doing big data, no one wanted to be small data, so everyone was a big data company, and even when it didn't really apply. So I'll talk about what I mean by big data. And the idea is that there's some spectrum of sizes of data sets, right? So my laptop here has 8 gigs of RAM. It's kind of an old laptop, but I like this old design. I'm delaying upgrading. And half a terabyte disk. And things that I can do on my laptop, I think, are safely called not big data, right? Anything I can do that fits in memory in 8 gigs of RAM, where the entire ML task plus, say, or any other task, right? Plus any transformations I do, if it fits into 8 gigs of RAM, I have a very hard time calling that big data. Some people will, by the way. Some people will call anything that doesn't fit into an Excel sheet or you can't visualize in an Excel sheet big data. But I think that's a pretty tough line to hold there. Anything that fits on my machine, it's a laptop, it's a personal laptop, I just wouldn't call it big data. On the other side, there's Google data centers, right, which are clearly big data. I mean, I shouldn't use just Google here. Any big data center, right? Big company operating data centers where there are hundreds of machines, probably many more, hundreds of clusters of machines, many nodes per machine. I have no idea how much RAM and disk they have in a data center. It's a whole lot. Who knows how many petabytes of data they actually store in these things. But clearly this is big data, right? So this is what we would call definitely big data. But then the question is, where's the dividing line between these things? And I think people often place it more due to kind of marketing, what they want their system to be big data, rather than actual sort of realities of any kind of justified division in the actual size of data. So there's no rule that says, at 1 petabyte, you are now big data, or as opposed to you aren't. So that's sort of silly to talk about even. But I do want to emphasize a few key inflection points that I think actually are quite critical here. So I sort of think of the hierarchy of problems kind of being divided into these 4 categories. And this is important because they actually necessitate different algorithmic approaches. And the MapReduce framework actually fits very nicely even into this last one here. So this is actually kind of a good motivation for why we use frameworks like MapReduce. So let's talk about this hierarchy here. The first level is that data fits into RAM on a single computer. And this, this is now growing, so we can actually get pretty big with some of these data sets. But this, I would still call in all cases definitely not big data, right? You can do all your processing kind of in memory. You don't have to worry about kicking stuff out and doing some stuff on disk, some stuff in RAM, et cetera. You just do all your analysis on memory in data. And by the way, 99% of all data science fits into that first category there, I would say. I don't think that that's an exaggeration at all. All the work you're doing in your projects, unless you have a very particular project, is probably of this type. So there's nothing bad about sort of this small data regime. I mean, we especially with larger machines in Amazon, you can fit on, or AWS or the cloud anywhere, you can fit a lot of memory data into RAM, right? You can get 1 terabyte RAM machines. They're expensive, but you can get them. But the model you use for processing data there is very different from other models, right? Because you just load all your data, do the analysis, and then print out the analysis or somehow store it, right? And like I say, this is probably where you should be doing most of your work in number 1. Even if you have a bigger data problem, you should actually do a lot of exploratory work in this first stage on a subset of your data, and only then, when you're really confident in your models, expand it to a larger set. So point 2 is where it no longer fits in memory, but it does fit on disk, right? So disks are much cheaper than memory. You can easily get many terabytes of disk space, even though that's pretty expensive for me to do for RAM. And so this now necessitates different ideas too. If I have a single machine, and I can't store my data in memory, but I can store it on disk. And so here, I might have to do things like read and write stuff, and do process data in mini batches, stuff like that, because I can't just load it all, analyze it, and then dump the results. But it's still things I can do on a single machine, right? I can still I don't have to worry about distributed processing of my different bits of different records of data. And so I can still kind of think about the paradigm being basically I have a big disk plug into my machine, and I just kind of run in that framework, right? And the third one is where we start, and I also wouldn't call that big data either. I mean, I would call that kind of, bigger, certainly, but not getting big yet, because I can still just handle it in the paradigm of a single machine, right? Now, it's definitely the case that sometimes, even when you have data that can fit into a single machine onto disk, you still do distributed processing to actually analyze it. This is actually very common in things like deep learning, where we are actually more compute bound these days. So, ImageNet, which was that image classification contest I talked about last time, that's only about 1 terabyte of data that they were using, and it's one of still the bigger data sets people commonly use for deep learning, at least that's publicly available. And so there's plenty of interesting distributed systems you can do with data that size. But the data itself I would not call big if it can fit on a single drive safely, without worrying about spreading it over multiple machines. So the third point would be when you actually have data that you really need multiple machines for right now. So either in RAM, if you want to do that kind of analysis in RAM across multiple machines, maybe big machines, maybe big memory machines, or even more so if you need multiple machines with different disks to store it. You have to store your data. You have to store your data in a distributed fashion because there's just too much to analyze on one machine or to store on one machine. Okay. But in the third category, I would say that you still have a relatively small cluster of machines. And what this means is you don't have to really worry about the machines dying. You can basically assume you're going to have these 10, 20 machines that are all storing their own bits of data, but you kind of just, you don't have to worry about them going down. They're going to survive these 10 machines, right? If you have 10 machines running, the chance of one going down is very small. But the fourth and biggest category here is where you really need much more than that to even consider storing your data, right? So you actually need, maybe hundreds or thousands of machines to store your data. And if you have 1,000 machines, they are just going to start failing. I mean, machines do just break, and you're going to have machines break as you're running operations. And this necessitates a whole nother set of tools you need. Just like this one, of course, also 3 necessitated going from a single machine to distributed processing. Number 4 also means we have to worry about things like data redundancy and how to handle machines that go down as you're doing a computation and things like this. So these are all pretty reasonable demarcations of different strategies you need when you handle sizes of data of different types. Now, I would personally sort of draw the line of big data at number 3, saying if you need to store it in distributed fashion, I would call that big data. Some people, I think, rightly would say it's only number 4, where you have to really not only store it across multiple machines, but have to worry about machines crashing and failing. I'm happy to say number 3. I would fight against number 1 or 2 being called big data. I think the term, as I said, is used too much, and so I would actually kind of argue against anything that's less than a terabyte, say. You can store it on disk on a single machine. That doesn't really seem like big data, actually, to me. It seems like maybe it's big processing if you're doing a lot of complex stuff with it, but the data itself is just not that big. I have probably on my own machine, close to the size in terms of images as ImageNet did. I just don't really think that's that big of a data set. It's big for machine learning, but it's not that big in terms of the data itself. Okay, so, or at least the ImageNet competition I meant that's used for deep learning. So this sort of question is a really important one to ask yourself then is, do you really have big data or not? And the reason why this is so important is that if you don't have it, if your data fits into a single machine, even on disk, you really can use very different methods for analyzing it. So this is actually a paper I really, really like here. It's by Frank McSherry, and it's called, and some others, and called Scalability, but at what cost? And I forget what cost, I think cost stands for cost of the single-threaded implementation or something like this. Can't quite remember, actually. So what they did here was they looked at a lot of sort of recent, and I should say there have been kind of rebuttals to this, and so you should take this all with a grain of salt. Don't take it as the final word in this space. But they took a lot of benchmarks people had used for demonstrating these scalable systems like Spark and Xstream and Giraffe and GraphLab and GraphX and this kind of stuff. So they took problems people had used to demonstrate the scalability of these platforms, how they could, not only could they process it quickly, but they could also scale, say, linearly with a number of, machines that are added to your system. They did this initially then compared to a very heavily I shouldn't even say heavily optimized, a well-written, but frankly not that heavily optimized, single machine implementation that, maybe had some amount of cleverness in some cases, either using only RAM or SSDs, but basically used a single thread on one machine. And they compared to these things. And what they found was that actually most of the reported results in the literature, if not most, and if not all of them, at least most of them, are actually quite a bit slower than a single machine with 128 cores, for example, are slower than the single machine running the same task. And so this is, I think this was kind of a nice jolt to a lot of the people that were very excited about some of these distributed processing frameworks, because the reality is, for a lot of the data that they were, and I should say, these things still have advantages too, but for a lot of the data they were actually using to highlight the value of these things, there just wasn't that much benefit to being distributed at all. You should just do a nice, well-tuned implementation on a single machine. So this is actually a really important point, right? That if you don't have data that really needs the distributed processing and the reliability and stuff of a framework like Spark or many others, you really don't want to go down the path of using them, because they're going to add substantial overhead when you plug them in. And, this hope that you can scale once you get there, once you get enough data, is often misplaced, because oftentimes you never really get there. You always have a relatively small amount of data. So this paper, I really like this paper. I would definitely check it out if you're curious about these things, because I think it really impacted sort of my view of this literature. Okay, so let me now, with that being said, let me give a brief. We are in this lecture, so with that being said, this lecture is going to treat the case of large distributed processing, or at least one framework for doing so. If we're going to talk very little about how these things actually work, we're going to talk about the programming model, or a programming model for actually using them. So the other thing I'll say is that it definitely is going to be about one way of solving these things, and there are cases where you do need these things. And we'll try to sort of move towards that today, or highlight how you can do it today. Okay, so I'm going to talk now about some sort of general context in distributed computing. There's a little bit of history, but also sort of putting these tools that we're going to talk about into the context of sort of a larger history of how people have dealt with massive parallel processing. I should also say that, actually, I meant to add one thing here. So I should also mention that the tasks we're going to talk about when we talk about really big data like this, like MapReduce tasks, they almost by necessity, big data tasks are actually relatively simple. So this is another important point to make. I talked last time about these things like deep learning applied to ImageNet and stuff like that, and I've just said now that ImageNet is not that big of a data set. So hence, the techniques that we're going to be applying here, by necessity then, can't be as complicated as training, a huge, they can for some cases, but not for many cases that you're really going to want to deal with, are not as complicated as training a massive deep learning system, right? There are things like counting the number of words, or building an index over pages, or traversing a graph, stuff like this, right? That are relatively simple at a small scale, but get much more complicated at larger scales. And that's really where techniques like MapReduce they excel. Okay, so let me talk about a little bit of some history of distributed computing right now. Okay, so distributed computing arose. It kind of came to prominence in the 70s and 80s, and it really was centered around this notion of sort of supercomputing, right? Often driven by things like scientific computing applications. So people wanted to simulate great big partial differential equations. The laws are actually quite simple and straightforward to write down. You just need a lot of computing power to actually do it. And so the natural way to do this was to, we're going to break this up over multiple different machines. We're going to solve them all, different parts in different machines, and then combine the results together. And this works really, really well for things like solving PDEs, right? It's definitely the way you want to do it. You don't want to try to solve a PDE in one system kind of in parallel. So there's actually some nice work done at CMU, the CMU C.MMP. This had 16 PDP-11 processors, which each of which were absolutely tiny. And also exemplified by companies like Cray, who had a famous line of supercomputers. This was the Cray 2 from '84, and it had 4 of these vector processors, which were really good for doing linear algebra. Right now, actually, a phone will have more computing power than this, right? But I actually think this is actually not a knock on Cray. I think it's actually amazing that in 1984 they could have as much processing power as a modern phone does. That's actually incredible because considering how fast technology like this has evolved, it's amazing that in '84 they had as much power as that at least I think in like various linear algebra tests, they actually did better on a Cray in 1984 than an iPhone does in the current day, or about the same as an iPhone does in the current day. Anyway, this was the paradigm for parallel processing and distributed computing kind of as it first arose. And at the time, when they were sort of developed, there were a lot of different ways of programming these things. So people had to do sort of manual synchronization of threads, communication over network to sort of manage these things. And this got kind of hard to do. There's a lot of sort of specialized ways of doing this. And so in the 90s, researchers kind of established or coalesced around a common interface for doing a lot of parallel, a lot of distributed multi-system programming. And then one of the most famous ones of these was called MPI, which stands for the Message Passing Interface. Who here has actually used MPI before? So maybe one person, 2 people I see this done. Okay. So MPI is actually, it's a set of tools that let you execute code processes over multiple, or let you execute multiple processes either on one machine or on multiple machines. And they provide a suite of kind of interfaces for common operations. So these include things like communication between the different processes. Also things like sharing data, so techniques like scattering or gathering, as taking data from one and sending it to many others, or taking it from many others and coalescing it back into one. Broadcasting, so sending a message from one process to all the other processes, as well as doing things like synchronizing the different programs. So you can be doing execution up to a certain point, but at a certain point you need to sort of collect the results from all the different processors. So you have to let them all finish, then bring them all back together, and MPI lets you do this. It's a set of it expansive set of primitive operations that let you do this kind of distributed processing. And I should say it's still very, very common in scientific computing applications. It still kind of is one of the standards for how you do basic kind of coordination of processes for distributed computing. Now, I should add, though, that its main downside, honestly, actually, I think I have a downside of this thing here. So it's very powerful, but it does have some notable limitations, MPI does. So the first one is it's actually quite complicated. And it's not that easy to just jump right in and start using, because you have to do a lot of things yourselves. So basically, you have to explicitly manage your data. For instance, if you want to share data across multiple machines, I have to explicitly set a way to, come up with a way to either load them from separate machines or somehow manage, farming out data from a centralized host to many other machines. And that gets to be kind of a pain when you have to do this many times for major applications. It's very hard to write kind of a short, simple MPI program that just does a data processing task. You would not want to use it, for example, in data science that much, because it really is meant for large-scale, massively parallel computing where you're really it's worth time to write it once so that you can solve your task, or solve your PDE or whatever many times across many different cores very quickly. So the first part is it's complicated. It is really kind of, I've worked in MPI a fair amount, and I still have to look everything up because I can't remember half the calls, and it really is complicated to use. Much better than what came before, from what I hear. I never used what came before, but certainly still kind of complicated. And the second thing is it's brittle as well. So unlike what came afterwards, MPI was not built for this regime where computers would fail. It was built for these supercomputers where you really, there were a lot of processors, but they'd all be kind of available, right? They would not just randomly die. You wouldn't have entire machines or entire nodes in your network that would just fall out, without any warning to the system. And so if you wanted to handle things like that, be robust to things like machines failing, you'd have to write that code as well. Now, of course, you can write any code you want in MPI. It's sort of a general framework for doing these things. But it's not trivial to handle these sort of tasks. And so into this sort of system, this sort of notion of computers that were always available, that really had the power to always be kind of running, companies like Google started coming around, right? And Google had a very different problem. They had a massive data set where they had all these different, really heterogeneous machines. So they would, put big data sets together of very different styles of machines that basically would be indexing the entire web, and they want to run processes like the PageRank algorithm over this entire database that they had gathered. And so and things they were also using for a while commodity hardware too. So machines were different speeds, they had different cluster sizes in different regions, this kind of stuff. This is actually kind of an aside, but the data itself was also distributed, so that their actual where the data was stored was also spread across this different cluster. And so it was also much more efficient, if you could, to actually run processes on the nodes where the data was, rather than moving data around too much and then running tasks. This is sort of point 2, I guess, of MapReduce. But this sort of setting here in general is very different from the MPI setting. So MPI, you're often creating the data, right? There isn't that much data because you're like doing a simulation or something like that. Here it's all data driven, so you want a way to not have to ship too much data around. And you have things like machines failing all the time. And you have, by the way, a lot of programmers that want to code on this environment, and you need a way to actually easily let them be productive in this system without teaching them all MPI, perhaps. So what this led to was the development of this MapReduce framework. So there's a famous paper in 2004 that introduced this framework. And it was later, and this was describing a system at Google at the time. So Google actually was the MapReduce system originally. But later it was made extremely popular through the Apache Hadoop implementation. And actually now MapReduce has become a general term that oftentimes refers more to Hadoop than anything going on at Google. I think that Google doesn't use much pure MapReduce at this point anymore. Okay, so we're going to talk about this a lot more, of course, in this class. But the basics of MapReduce is that programmers using MapReduce just have to write two functions, what are called a mapper and a reducer. We'll talk about what they mean in a second. But if you write these two things, and it's sort of a simple framework in some sense, people can get used to it very quickly. And then once you do it, work can be automatically farmed out to a large collection of machines, while handling things like machine failure or machines that just for whatever reason take a long time to compute their solution. And as much as possible, computation is sent out to the nodes such that you don't have to move data around. You can actually move the small bits of code you use rather than trying to shuffle the data itself all around your network. And so this came about almost 15 years ago now, MapReduce. 2004 was the paper. And since then, and it proves kind of it proved an amazingly effective paradigm to kind of start doing a lot of these big data tasks that were genuinely big, that really needed this kind of power to and sort of robustness to really handle the size data we're talking about here. But it also is true that this is not sort of the end of the story. So since MapReduce first came out, there have been endless attempts to improve upon it. And so many of and we'll talk about the advantages shortly, actually, why these things are doing it. But there were lots of things that are kind of not well suited to modern tasks that were part of MapReduce. Things like the fact that you would read and write from disk after every single operation. You would do every single mapper operation would essentially read and write from disk. And this is, of course, not going to work when you have large, kind of complicated pipelines, as you do in most modern algorithms, or a lot of modern algorithms. And so we've sort of been, moving kind of away from pure MapReduce as a community of, as a data science community. And really, I think, in some sense, it's kind of a slow reintegration, a lot of the ideas from the high-performance computing community, which is sort of where supercomputing and distributed computing started. So things like GPUs, actually, I would say, are kind of a more natural continuation of kind of the HPC line of thought than they are of the distributed computing line of thought. And so I think a lot of the current work involves thinking about how we integrate kind of the best of both worlds in these two regimes. And so finally, a last thing to remember. I guess there's some ways. Sometimes this one here can switch. But when you do data science, actually one of the most important things to remember, and start thinking about distributed computing, one of the most important things to remember is kind of the hierarchy of speeds that you're going to encounter. So reading, if you have tiny data that can fit in cache, that's going to be really fast. After that, RAM will be faster than that, or slower than that, but a whole lot faster than disk. And disk is typically also itself much faster than normal network. I mean, there are networks that are faster than disk that actually can flip. But for most tasks that you're doing as a data scientist, one of the best things you can do to sort of be practical is remember this. And so when you have to do things like send, if you're writing code that's distributed, but you're sending around massive amounts of data, you're not going to make very good use of your distributed computation. You're going to be actually wasting your time. So things like this, using the fastest storage mechanism possible is going to be an important thing to keep in mind if you do need to go to the regime where you're actually doing distributed computing in this space. Okay, any questions so far? This has sort of been pretty high level, but we'll jump into the details next. No, network and disk can switch. The question was, is this always true? So network and the rest are always true. Network and disk can switch. There are some networks that are faster than reads off a disk, but the networks that you're using, this is true for. So the networks you typically use, downloading anything off the internet, for example, this is definitely going to be true, right? So it's only potentially very local networks that can be faster than disk. Other than that, this is true. Okay, so let's talk about MapReduce now. And I'm going to introduce it by talking about actually map and reduce, which is not the same as MapReduce. MapReduce is one word. It's capitalized, usually the reduce term. But you might see it uncapitalized, the reduce term too. But as a way of introducing it, it's not bad to think about these map and reduce primitives. But we'll talk about in a second the differences between this and actual MapReduce. So MapReduce, again, are two built-in functions in Python. Actually, reduce was taken out of Python 3 as a default function, but you can import it yourself from the func tools module. But what they do basically is they're two calls to operate on lists, or more generally kind of iterables, right? This is sort of, or iterators. This is sort of how Python treats things that, are like lists, but we haven't been instantiated yet. So what map does, and they're really incredibly simple operations. So you probably, if you haven't seen them before, you can understand them in a single slide. So what map does is it takes as input the map function, takes as input a function f, and then a list, or an iterator, and outputs a list, or really an iterator, of that function applied to every element in that list. I'll just say list for now because it keeps it a little bit simpler, but when I say list here, I really mean, I could just easily mean an iterator or something like this, that it hasn't been instantiated yet. Because that's map. Take a list and a function, output a list wherever you have that function applied to every element there. What reduce does is reduce takes a function and a list and iteratively applies the function to two elements at a time in the following manner. So first it takes the first two, it applies the function to it, g. Then it applies the function to the result of this, and c, etc. What this means, of course, is that the output of the function has to be the same as its inputs. So the input to the function takes two inputs, and it has to output one of those inputs as well. So you can keep chaining the functions like this. So for example, here's a quick example in Python. I have some data. I guess I've imported the reduce library here already in a previous cell. So I have some data. I have some values, and my values, what I do to create my values, I apply a map function where I'm applying a function that will square the input to that function, and applying it to data. So the output of this will be, again, if I make it a list, it will be all those elements in data squared, so 1, 4, 9, and 16. And then the output, to get the output, I use the reduce call on a function that takes two inputs and adds them together. And then I apply it to that list, and that just adds together all the elements there. So the output is 30. It's the sum of all the elements which have been squared. Okay, so the way to think of that kind of graphically is just the following. So map takes the inputs and just creates a list that's the same size by applying the function to all those elements. And then reduce kind of sequentially generates a smaller thing by taking all those inputs, so all those sort of mapped values, and then applying them sequentially to the results to each other to finally arrive here at a last single output. Now, it doesn't have to be a scalar output. It could be like a vector here. You can actually return a vector of things. But you can think of it like a scalar, right? It's no longer a list. It's just a single output now. Okay, so that's what what reduce does. Now, what you should also be sort of thinking about, of course, is that you don't have to do them in this order, of course, right? I could also take the last two and build like a tree structure here. Python will just do it sequentially like this, I should say, in the reduce call, because if you're not being parallel, there's no real advantage doing it any other way. But you could structure and order these reduces differently to somehow change your order of operations. And this is actually exactly what we'll do in the distributed setting. So there's finally some terminology I want to add here, which is the notion of a mapper. Now that I have these sort of notions of map and reduce, I want to define what I mean by a mapper, a reducer, and an execution engine. Okay, so a mapper is the function that you call map on. So in this case, the mapper would be the function f. It's the function you actually apply, pass to the map operator. The reducer, similarly, is the function you pass to the reduce operator. So in this case, g would be the reducer. And so when you are writing code in a MapReduce framework, you will write a mapper and a reducer. Typically, you will not write the third part, which is the execution engine. This is the part that's responsible for actually executing the map function, the outer map function and the outer reduce function, and that is handled by, Hadoop or Spark or whatever, or Amazon Elastic MapReduce, right? That's handled by some other thing that you really don't want to write because that's kind of the hard distributed systems part of things. You just write the mapper and the reducer, and you're done. So, for example, this is a very simple map execution engine. It literally just calls the Python map function, then the Python reduce function. But here I have a mapper function, which is the mapper function that squares terms. So I can take an input and return that input squared. I have a reducer that adds terms, so I take two inputs and I return their sum. And then the way you would sort of call like a MapReduce program is that you would pass the data that I'm going to run it on, the mapper and the reducer, to my engine, and then that does all the actual internal work itself. Okay? But of course, you wouldn't write this thing here. You would pass this to sort of a real MapReduce type engine, which we'll see at the very, very end how that can work in practice through some Python libraries. But do all that terms make sense? Because that terminology is important. That the mapper is the function you pass to map, and the reducer is the function you pass to reduce. And the execution engine is sort of the thing that glues it all together. Okay. Now, the key point here, as I emphasize, is that if you're to use a framework like this, then you as a programmer only need to implement the mapper and the reducer functions. Okay, because everything else is handled by the system. So if I want to process some large amount of data, I just write what's the function I want to apply to every element of that data, and then how do I kind of combine different parts of these results together? What's the output that I actually want at the end? And the nice thing here is that there's a lot. If you only restrict yourself to sort of optimizing those two things, there's a lot of optimizations you can apply after this. So for example, in this instance, I guess the mapper functions are always going to be inherently parallel, right? Because you can always just run all those things in parallel. So if the F functions themselves are very compute intensive, say that they do train some sort of small system or have to solve some large set of linear equations, something like that, this framework is nice because you can inherently do that all in parallel, right? By definition here, there's no sequential nature to the actual mapper stage here, the map stage, and so that can be done always in parallel. Okay, so that's sort of point number one. And point number two is that sometimes, depending on what the reduce function is, some of that can also be done in parallel. And in fact, for any practical MapReduce framework, you want to define functions where the reducer can also be done in parallel to a certain extent. So let me give a quick example of this. So here would be one instance of how you could write different execution engines. One which was inherently single machine, and one which was inherently parallel. So here's how the single machine execution engine works. Basically, it's pretty simple. I just call a mapper that generates the maps function. I call a reducer that generates a single output. Right? This is exactly what we already saw. So that is just this. That's this code right here. Right? This is the single machine execution engine. But of course, the nice thing about this is there's no need to just do this, right? I can also create a distributed execution engine that, under the right assumptions, and you almost always satisfy these things, will generate the exact same results as that single machine one. But if your mapper or even if your reducer in some cases are particularly complex, take a long time themselves, this can be much more efficient. So if the mapper was load some data, perform some complex transformations on it, and then output a simple result, that would actually be well suited to this sort of distributed framework. So here I have maybe some master node here that has all the data, or in fact the data itself can actually live on the workers to start with. Maybe I just sort of passed like a pointer about which bit of data that they should use. But think about it for now, it's just the data lives on this sort of master node. And it sends it to a bunch of workers. It sends a sort of part of this data to each of the different workers. Again, I can do this because this is sort of a portion of this big set of data here. I'm fine to do this because I can execute all my map functions in parallel. Then each worker applies the mapper function to produce a set of data where the function's been applied. And then importantly, it locally runs its own reducer. So it reduces everything. It computes its sum, say, locally, in just a sequential manner, like you would in this one here. Right? It just computes its sum locally. And then it sends, and then the reducer sends all of these to the master here, which runs the reduce function on this combined set. Now, it's important to know why we're doing this, right? Because you don't have to, and maybe if the mapper was the most complex part of all this, you maybe could just send all the data back after the mapper to the master, and then do a reduce operation. But in a lot of cases like this one, or I shouldn't say like this one, it's just a hypothetical example. But in a lot of cases, sending data back and forth is costly, right? So you don't actually send the data from the master to all the workers. You just sort of point them to some location on their own disks, maybe, where they have the data. And then similarly, you don't want to send all the data after it's been transformed by the mapper. You don't want to send all of it back to the master node, because that also is costly. It's going to take up a lot of network bandwidth that you don't want to sort of spend time on. So what you do is you first run the reducer. I first compute the sum for each worker individually. I just send those sums back to the master, and then I add those up last two. So you can think of it kind of like, instead of just doing this thing, I sort of do this kind of in mini for some subset of the data. I have these things. I send all of these back to the master, and I add those things up in the same way, same kind of reduce framework. We'll talk about more complex versions in a second, but this is the basic paradigm, right? Is that you can kind of do this stuff. So you can, be kind of naturally distribute this out. And the reason this works is that because I'm a mapper and a reducer function as a programmer, all the sort of detail about how I ship things over and how the parallelism works is handled by the execution engine, not by me. So I can let Hadoop or Amazon Elastic MapReduce, I can let that all be handled by this. So quick poll now. Okay, so the question here is, when the basic question that I actually want to ask here is that for this example, when will this actually work? Put simply. So suppose that my data splitting process here is completely random. Okay, so I just I randomly assign examples to the n different workers. Yes. Question. Question is, doesn't mapper split the data? No, mapper does not split the data. Mapper is the function you apply to each element in your data. So in this example here, the data is each of these 4 values. Mapper would transform them by squaring each of those. Mapper does not split the data. The execution engine splits the data, handles all that kind of stuff. But the question is, if I were to run this thing, in the fashion where, say, my data splitting is done randomly, right? So I just would randomly assign each data point, each element in my original list to one machine. What is required for this to actually work, right? And to give the same results each time? So this is actually it's more than, you can answer more than one thing here. Hopefully I got that right in the poll this time. I should check that. Let me check really quickly. You can, yes, good. This time is actually multiple choice. So which properties of the mapper and the reducer are required to ensure the results are deterministic? So I have 3 sort of general properties of functions here. The first one is that G is commutative. So you have to be able to basically say that G of A and B equals G of B and A. So a mapper or a reducer that would add 2 numbers would be fair here, but a mapper that subtracted the second from the first would not be valid here. Also, that it's associative. So if I apply G to G of A and B and C, this is equal to the same as G to A and G of B and C. So I can basically do, I can kind of put parentheses effectively around different locations as I want to. And the last one is that F and G are distributed. So that if I take the result of my mapper or of my reducer and apply the mapper to it, this is the same as if I take my reducer applied to the mapper applied to each element. So the question is, which of these are required for this thing to work and give the same results as kind of the single machine version that I showed? All right, so I'll open up the poll. Okay, so most people said they need to be commutative and associative, and they do not need to be distributive. All right. Let's take actually the one that's most controversial. I guess that would be this one, barely. Does anyone want to argue for or against being distributive? The thing being distributive. It's actually one of the harder ones. Maybe we'll start actually with the commutative one. So we'll argue why it is or is not necessarily this commutative. The reducer has to be commutative. Actually there, in the blue shirt. Mm-hmm. Okay, so the idea was, yeah. So that's exactly right. So I mean, the thing to think about here for this one is essentially, if I have a list like this, 1, 2, 3, 4. Say I send these 2 to my first machine here, and these 2 to my second machine. 1 and 2 and 3 and 4, but they're sent randomly, right? So this has easily been 1 and 2 and 2 and 4. So whatever, I'll map them. I'll map them to f of 1 and f of 2. But now I'm going to apply my reducer to this, right? My reducer to f of 1 and f of 2. Okay, and if this here, but there's no inherent ordering to this thing, right? I could just easily have swapped these 2 things, and I should get the same results. So if I swap them, and I get different results, and this whole node will return a different thing. And of course, you can see that the entirety would return a different thing too, right? If I'm reducing them at the very end, just the results of this one I reduce down to here. If this whole result, we could just easily, for example, swap these whole 2 machines, so that this one goes to the first machine, this one to the second machine. And this is not commutative, then the order here is going to depend on which machines you send them to. So it has to be commutative to actually work. Yeah, question.
I don't see why there's a point in when you're setting the data, setting them in different order than they come. For example, this array could be contiguous in memory, so it does have an inherent order. And then in the end, when you call reduce, it's also very easy to just take input all the map results.
Yeah. So I think the question is why not just order them the way that it is, and tell each system that it's ordered this way, et cetera. So there are actually some very good reasons for this from a management of data standpoint. So remember that the whole idea of MapReduce is we wanted to break this down into tasks that could be done kind of without a concern for the larger, broader system that was being executed in, right? So if I have a bunch of records that I want to then transform and somehow combine, I don't want to care as a programmer, someone writing the MapReduce the mapper and the reducer, how those records are stored on disk, right? I should not be able to write any logic where if they're stored in a different order or they're somehow stored differently on disk, this will affect the results of the computation, right? That actually is sort of a power we don't want to give the programmer because it makes it much simpler if you don't have to worry about that. And there are also things that are sort of more practical, like machines will die. If a machine dies, you want to somehow rerun all the information that was on that machine. And so then you have to spin up a new machine and get data that was on that machine before. Or maybe you don't want to spin up, you want to transfer data, so I have to find other machines where that data already lived, and now I'm doing this all out of order in a very sort of unordered way by default, right? It's not as easy in the setting of all the things that could happen to maintain things like order the data. It's a strong constraint that we don't want to have to impose on our data. And so this is why you don't want to actually require this of a MapReduce execution engine, and you certainly don't want to make assumptions when you're of your programmer that they actually have to code in this way to assume something about the structure of the data itself. Did you have a quick follow-up?
Why can't the programmer just specify whether this operation is commutable or not? Because so you have a group. The number of the median groups is really small, and most of the operations that you want to do are not commutable.
So the question was, most operations you do undo are not commutative, but I don't know. I mean, so what reductions do you when you have a whole collection of data, which is inherently unordered? I mean, it really should be inherently unordered. This kind of data. You're talking about records, right? What are the cases where you really do want to, if they are unordered, they are unordered, right? Now, if you have data that is inherently ordered, what you should really do So you have data that sort of is ordered, right? So like this really starts there, this starts there. What you should do, the way you handle that is you don't, what you would do is you actually specify something in the data itself that says what the order is. So, basically this part of the data is here and this part of the data is here. And then, so for example, if I were to sort of also say among these things, what position of the data they are. So this becomes, 0, 1, this becomes 1, 2, etc. Then I could have a reducer that would actually look at the first thing as being kind of the order of operations, and so it sort of would know where in this sequence it was. But that's what you want to do. You don't want to require somehow the execution engine to know about this. You want to actually specify things like order or other meta information as additional properties of the data and let the reducer sort of work on that. Because if I have a reducer that sort of says, subtract one from the other, or subtract the first one from the second one, right? I could do that by specifying two parameters for each thing and sort of saying like what's the order of these two things, and then that would actually be commutative because even though it's sort of a non-commutative operation fundamentally, it's still commutative in that I just check which one is lower and I subtract the lower one from the bigger one. So you can always kind of capture any non-commutative behavior you want to in a commutative operator, and that's why typically it's done that way. There was one more question. If G is a power function? Yeah. Mm-hmm. Yeah. Right. So x to the power y would not be a commutative function. And so therefore, it would actually change the operations. Depending on how if the data is far different, it would change the result, which is not something you want. You don't want that. So you don't want to use a non-commutative operator. Yeah. All right, what about number 2? That one everyone said was associative. Yeah.
So it works the same way, in the sense that since you're doing 2 operations and then a third one after that,
Yeah.
you want it to be in such a way that even if the orders are flipped, it still works the same way.
Yeah, exactly. So basically, if you get this, so for 3 now at 1, right? If I somehow do like G of 1. G of 2, or really usually it runs this way, right? So you get like 1, 2, 3, and that would do G of 1 and 2, and then apply G to 1, 2, and then 3. But of course, if you just had a different order of getting the points, the same exact thing, you could just easily have, how would this work? It would be like G of 2 and 3, and then G of 1 and that, which by commutativity is the same as if you did this ordering like with G around these two, and so you of course need them to be the same way depending on their order. So yeah.
Isn't there couplings between mapper and reducer in which they will actually fix this order?
Isn't there a what? What's the question? A shuffling. Yeah. So the question is there a shuffling in the mapper and the reducer? Yes. So some execution engines will implicitly perform a shuffling. But that is a choice of the execution engine itself, not necessarily a specification of the MapReduce sort of paradigm, right? It is, and certainly that may be a specification of the MapReduce capital paradigm, not of this map plus reduce kind of thing I talked about. But what I'm talking about here applies to this, this framework of map plus reduce as functions, not thinking about MapReduce. If there is a shuffling, this is not a requirement. So no, these are still requirements if there's a shuffling. Because if there's a shuffling, you have to be able to get the same result no matter what your shuffling is. All right, so what about the last one, the distributive property? Yeah.
The sum of squares is not equal to the square of the sum.
Okay. Mm-hmm. Right. Yeah, so the example I gave is not even distributive. But even more than that, actually, it doesn't even necessarily make sense to talk about this, right? Because you don't necessarily know that the output of your reducer is something that the mapper can take as input, right? There's no necessity for that. The mapper could take in, a keyword and does this, because it's complicated as one. It could take a keyword and do a web search on that and return, some information from these web searches. The reducer is a separate thing. So you can't interchange the order of mappers and reducers like this. There's no sort of sense in which that makes sense. So it does not need to be distributive. And our example, in fact, was not. Yeah?
it might be a good idea to like reduce some first before mapping, right? Because then it'll be faster.
So the question was, if you do have a distributed operator, would it be useful to reduce some first before mapping more? I'm not actually convinced that's true. I have to think about it, but you're still doing the same number of, you're still doing the same number of operations, right? Yeah.
So now, so then, like, if that, let's say plus and square is distributed, right? And you did 2 squared,
Mm-hmm.
did you reduce first or only 1 squared?
Yes, that's true, but that's not the MapReduce. So yes, I guess there could be cases where you could do that depending on like the speed, I guess, of things. But again, it doesn't really make any sense because you can't reduce the things that would make it a lot faster. Typically, are things you couldn't reduce anyway. So you can't reduce web terms and then you have to reduce them. Combine those before you run like a mapper of all these things, right? So in most cases, it doesn't really make sense to talk about these things. And certainly in the MapReduce framework, this is sort of a moot point because this is not the framework that it is, right? The mapper, the reducers are not interchangeable in this way in general. Okay, so let me move now, since we're running a bit slow on time. Let me move now to the actual topic you will encounter, which is not this notion of map plus reduce. It is actually the MapReduce paradigm. So the big important thing to remember here is that MapReduce does not equal map plus reduce. So MapReduce means something very specific. What MapReduce is, the way you should think about MapReduce is you should think of MapReduce as map and reduce kind of in quotes by key. So I'll describe what I mean by that in a second. But the big thing there, let me put this back. The big thing here is that the mapper function does, in MapReduce, and I'll try to sort of say MapReduce like that is one word. I get emphasis on the first syllable, just to keep it separate from this notion of mapping and reducing. You can think of MapReduce as this notion of map and reduce by key. Okay, so here's what I mean by that. What I mean by that is really 2 things. So the mapper functions in MapReduce, they don't return just a value. All right, so they take their input and they transform that input somehow. But they don't just return the transformed input. They return key value pairs. Okay? And so I'll describe what I mean by that in a second more, especially best with an example. But they're required to do this. They have to return data in the form of a key value pair, key value tuples, essentially. All right? So that's sort of number 1, is that the mapper. And this could be things like, and they can actually return more than one thing sometimes. But the way to think about this is that they sort of get some collection, and they return some list then of key value pairs. So if I were to, I'm trying to think of an example that doesn't, think of an example that's not word count, also doesn't give away the homework, which is always, which is also sort of I always get tied into one of those 2 examples whenever I try to describe it. But if I were to input something like a web page as my key, or a web page as my input to my mapper, then it could return a list of words plus the number of times they occurred on that page or something like that, which is key value pairs. All right. So again, mapper functions return a list of key value pairs. Okay. So that's the first big difference, and we'll see what I mean by that in a second. And the second thing is that before calling the reducer, the execution engine will always group things by keys. Okay, so this notion of sort of grouping by keys is fundamental to how MapReduce works. Okay, so let's see a quick example of this. So normal map plus reduce. You have your items, you transform the mapper to some new value, and you reduce them to give you some output. Okay, so that's pretty straightforward. MapReduce is not quite so simple, and we'll see an example in a second, which hopefully makes it a little bit more concrete. But this is sort of the big thing here. So in MapReduce, you have items, and you apply a mapper. And what the mapper does is it returns key value pairs where the keys can be the same across different things here. So I'm color coding them by color here. So this key is the same as this key is the same as this key. And you have the key here and the value, and the key here and the value, and the key here and the value, key here and the value. What the MapReduce execution engine then does is it groups similar keys or groups identical keys together. So it will internally, using also distributed computation, but this is never touched by the actual programmer. It will group them together. So the key will, the green key will have both value 1 and value 4, and the yellow key will have both value 1 and both value 2 and value 3. And then the reducer is only applied by key. So I will only apply my reducer to this set of values for the green key and this set of values for the yellow key. And my output will actually be a list of key value pairs too, which include the reduced value for the green key and the reduced value for the yellow key. Okay? And so this is just what the MapReduce paradigm says. And it's actually a little bit confusing, right? Because it doesn't really, why are you doing that? Why is this the formalism? Well, to a certain extent, it just is. This is how they work. I'll talk about sort of the canonical example in a second, which is counting words in a document, which will hopefully make a little bit more sense. But this is what MapReduce does when it talks about a map and a reduce function. Okay? All right, so let's talk about how this would work in the setting of a word count example. All right, so this is all my examples today and yesterday deal with, I guess, young children stuff because they're on my mind a lot these days. So this is a song that I hear way too much these days. Wheels on the Bus. And suppose I wanted to count the number of occurrences of words, of each word, right? So each, return a set of items that are the word itself and how many times it occurs. So, wheels occurs a lot on this song. Round occurs even more than that. The way MapReduce would work here is it would first sort of chunk the data up into some unit, for example, by line, right? So there would be all these different elements here, which would be then split up by line. And I would apply the mapper function to each line individually, okay, in my function. So I take each function, I apply, take this whole thing, break it down by line, and apply the mapper. Of course, it doesn't have to be a line. It could be by, by some logical chunk of text. As long as it's not in the word boundary, that would be fine too. After the mapper is executed, what the mapper does is it returns a list of key value pairs. And there can be repeats here. So we'll return a list of key value pairs that basically say, for each element here, the key is going to be the word itself, and the value is going to be number 1. So basically, it recurs one time each time. I could go a little bit further here and say, internally, if the mapper wanted to, it could already reduce things so that V would be V and 2. But let's just say that we're going to process it in the naive way. And so you have, for each key value pair, you have the word, and then it just occurs one time. All right, so this is after the mapper. You have this. So this is the function you write. You basically write a function that says, okay, I'm going to split the data into words and tuples that say, or key value pairs that say the word and then the number 1. That's all the mapper has to do. The execution engine then, the MapReduce execution engine then, will now group them by key. So what it will do is it'll actually take that result there, look at all the keys that are shared across all the returns, and then group them together. So I'll have, and then 4 ones, because there's the word and there with 4 ones, and so it'll take, the values after them and append them all together. Okay, so this is what I have here. I have, and, on, all, etc., round with a lot of those things. Then the reducer is run only on, per key, it's run on the list of all those values that it has. So I run the reducer on this thing, and if my reducer is, the sum, for example, it will just add these things together, and so I would end up with the pair and 4. It will add these things together for round, so it'll end up with the pair round and 8. Okay, and so this is sort of the mechanism by which MapReduce works. And again, why is it like this? Well, there's a lot of tasks kind of like this that deal with where you want to have this sort of grouping together by key, etc. But I think the reality is, look, this is just how MapReduce works. This is how it was set up, and you have to sort of get used to this paradigm when you want to use it. So let's see how this might work as an execution engine. Okay, so here's some simple code that basically, that's the question over there.
So in the previous slide, can your mapper be actually counting how many times each word occurs in the line and the result is the same?
Yeah, that's a great question. So yes, the mapper could, if it wanted to, also do a count itself internally. And in fact, a lot of, in Hadoop, or really most real MapReduce engines, we'll talk about in a second, they actually do that. They actually run like a mini reducer before it runs the big group reducer. It runs like a mini reducer on each element, each output separately, or on each machine sometimes separately to sort of speed these things up. But yes, you could. You could do that also just directly in the mapper. You could actually count and have a pair that said the and two. And then when it grouped by key, one of these would be, there wouldn't be 3 of these. Like 2 of them would fall out. It would have a 2 instead. But the sums would all go through the same way. It would all still work, right? You would still get valid results. And so it would be a perfectly reasonable way of actually doing that. Yes, it would. OK, so here is sort of the way this was actually kind of called in practice. So here's a very simple a MapReduce execution engine. It's more complex than the simple just apply map and apply reduce, but it's still very simple. So I first take my data and I apply the mapper to all of it. The output now is going to be a list of key value pairs. So what I do now is I create my, actually it's a list of lists of pairs, I think. OK, so I iterate over all my values, and then I iterate for each of those. I iterate over key value pairs, and I now start grouping things. So basically, if my groups is my collection of all the different words in the last example. So if this key is not yet in there, I'll create a new thing that has just that value. But if it's already in there, I'll just append that value to the end. And at the very end, my output is the reducer applied to all those things. Though actually, I think it should be k/reducer for all those things, now that I think about it. So I actually a typo even in that code. But this is a very simple, it's actually for return like key value pairs for all those things, not just the reducer applied to those things. So essentially, I guess you could, if there, maybe I actually had the reducer here. Oh yeah, sorry, I actually had the reducer return the keys too, so this is actually correct. So this is a very simple execution engine that calls MapReduce. There's no point in doing it this way, of course, because we'll just be doing it in parallel. But importantly, here are the actual functions you would write as the MapReduce, working in the MapReduce paradigm. You would write a function that basically returns, given a line, it will return word and 1 for all the words in the line. And then the reducer would return a pair of the key, and then you would just sum these things together. Now, you could also write a reducer that was more complex than that actually did this kind of iteratively. But this kind of thing, this sort of mechanism for doing the reducer is sort of the more common way of doing it, where you don't think of calling the reducer iteratively actually once you actually have all the data for a pair, you just compute the total result. Because frankly, it's a lot simpler than like actually doing these sequential reduces in the normal way. So this is just how you would call it. You basically have this set of lines here that have the text. You could call it our/MapReduce execute, and this would then return a list of word/count pairs for the whole thing. Okay, but importantly, if I as a programmer writing it, I wouldn't have to write this part here. I would just write this part here, those 2 lines of code, and I would be done. I'd have a way of doing this. And although this, executes it in parallel, or sorry, in serial, the idea would be that if I had a very, very big document, I could actually do this on a massively large document because I could run this all in parallel using data that was stored. If my document was stored along different places in the cloud, I would actually be running it at those places natively, and so it would be much faster than if I were to just try to move data around and do like a sequential count and stuff like that. Now, a couple sort of quick points here. MapReduce is not quite this simple, actually. There's some more advanced usage. So one of the things is that the input data is actually also typically in key value pairs, just a little different kind of key value pairs. And so maybe you have like line number / the text of the line, just so that they're always thought of as being key value pairs, all steps along the way. And this also lets you do things like chain multiple mappers together. This is which is sort of a very common thing to do. There's this notion of actually two types of reducers, one that's called combiners and one's called reducers. So combiners is actually that thing that runs directly after the mapper. That kind of does a mini combination like we were talking about before of just counting the words maybe within the line. And you can also sometimes run reducer combiners even locally on the machine before running a major reducer, and that also can work sometimes. And finally, there is the ability for functions to share some context. Because if you think about it, I mean, this model is very limiting. That's actually kind of the benefit of it, to be honest. It is limiting. And so there have been ways to add things like shared access to, say, read-only memory. Or even more things that are complex like that, like actually share some shared context between two different threads. But typically, you want to keep it as simple as possible. That's the whole point, in fact, of the MapReduce framework. Okay, so the interesting thing here is that, and I like putting it this way, is that MapReduce is not popular because of what it can do. It's not popular because it's really powerful. It's popular because it's not very powerful, kind of ironically, right? So MapReduce is popular because of what you can't do. Namely, you can't do much to screw up this sort of parallelization of your process, right? You can't write any code there. They will make the result incorrect if you run it in some other way, right? Because you just write these two functions that have really nothing you can do. And in fact, we weren't even really defining here reducers that are quite things reducers that are commutative in the same way before. We're just actually summing the things directly. So there's very little you can do here to actually screw it up. And that's actually the reason, and at the same time, it's also quite simple, these two functions. And so the reason why MapReduce became so popular, I think, is precisely that it takes most of the challenge out of distributed computing, lets people write very simple tasks, and lets them then run it in a distributed fashion in a hopefully effective manner, right? So there's no exposure of inter-process communication, data splitting, data locality, redundancy. All these things that are key to distributed systems are all hidden from the user. And they're allowed to be hidden because we're incredibly simple in sort of what we're allowed to do. So it's popular because it's not very complicated. It's not very powerful, right? I.e. what you can't do, i.e. what you don't need to do, right? You don't need to handle things like inter-process communications like this. A lot of subsequent follow-on work to MapReduce, so things like Spark, which does in-memory processing for MapReduce tasks, and does other stuff too, has more complex operations as well. These things actually typically add more primitives, but they do so at the cost of much more complex code you have to write. And so, while I think some of these things have started to become more accepted and kind of more standard these days, pure MapReduce actually really isn't that common anymore. It did have a huge advantage to being very simple, and therefore you would not need to follow all these sort of rules that you have to follow in more modern architectures to make sure your data doesn't get messed up somehow. So these are actually the advantages here. But on the flip side, it can be extremely slow. So the downside of MapReduce, and I think this is actually what's kind of causing it to lose favor currently, other than for a very specific slice of applications, is that it actually is fairly slow. So for example, in traditional MapReduce, it achieved resilience. This means that it achieved the fact that machines can fail or go down and things don't really affect it. By doing things like reading data from and to disk after every iteration. So if I failed during the middle of a call, I just throw out that process and then start a new one because I've read I've written the most recent result to disk and then everything's fine. In systems that don't have that, writing to disk from disk every time, they had to do very complex things like save chains of computation that would lead to an in-memory process being exactly in this state. So this was made it very simple and resilient, but it also meant that it requires a lot of disk reads and writes. That's a slower type of data processing. You sometimes really do, and also it makes it very sort of badly suited for things like iterative computation, where I have to take the results of one thing and immediately apply some other transformation. If I'm reading and writing from disk every time I do that, that's pretty slow. It also means you really do sometimes want communication between processes, right? MapReduce does not allow that in its fundamental form, and you really do want that sometimes. And so this has led to a lot of other paradigms for distributed computation, things like Spark, GraphLab, parameter servers of all types. I guess new things like Ray is a new sort of paradigm for this kind of stuff, or a new framework for these kind of things. But there are many, many other frameworks for these sorts of tasks. Now, while these are much better than core MapReduce, I just still want to repeat my point that all of these are typically going to be slower than, code that you can write for a single machine if your data fits locally in RAM. Right? So this is going back to the start again. So it's great that you have frameworks like Spark that can scale to many machines, be resilient in memory, this kind of stuff. Do not try to use Spark on a single machine hoping it will be faster because you have a little bit more power from parallel processing on your 4 cores. Right? It will not be. It will actually add significant overhead and typically be slower than if you just do these things yourself. So the last thing I want to say is, just to give one example, and I'll actually just end here after showing this slide. All I'll say here is that when you use Python, if you want to use Python in practice for doing real MapReduce, use a library. One of the more common ones is called mrjob. I don't know if it's pronounced Mr. Job or not, but it's MapReduce job, so I've never actually heard it said before. I just always call it mrjob. MRJob, which is a library for writing simple mappers and reducers as Python classes. So I can have a class called like word occurrent count, define the mapper, define the reducer. It uses the Python yield keyword as a way of sort of handling returns of key value pairs. So I yield key and value pairs. And the reducer also yields a key in the sum of the values. And so you have to sort of use this framework. But the nice thing here is that this mrjob includes interfaces for Hadoop and for things like Amazon Elastic MapReduce and stuff like this. So if I write my code using mrjob, I can actually execute it on multiple different execution engines, kind of all with the same class in Python. So this is, again, the advantage of MapReduce. You write things like this, not things like, not things that care about interprocess communication or distributed computing. You just write this. But with this sort of simplicity comes some costs too. And so it's a very powerful paradigm, but a lot of what you want to do in data science doesn't always fit into this paradigm. So be careful about when you apply it and when you don't apply it. Okay, I'll see everyone Wednesday. The homework will be released on Wednesday, and I'll mention a little bit more about that in class on Wednesday.